It's Saturday, the 11th of January, 2020, and this is Nighttime Mathematics Radio. Well, it's that time of the year when students everywhere turn their minds towards optimization problems, and boy, howdy can they be a mess. So, got a few of them came in before the program even started, but for the moment, this works the way it always does. You can tweet your problems to @NightMathRadio on Twitter, and I'll try to solve them here live on the air. This is Nighttime Mathematics Radio. I'm going to take about a 2-minute pause here to let people tweet in any math problems that might be weighing on their minds, and when the 2 minutes ends, I'll come back with a few problems people asked between the two shows. Good evening, everybody. Alright, everybody, this is Nighttime Mathematics Radio. Let's take a look at some optimization problems that have been giving people trouble over the break. Now, the first question we got asked looks like this. We've been told, let me pull the problem up here, that Jane is 2 miles offshore. In a boat and wishes to reach a coastal village 6 miles down a straight shoreline from the point nearest the boat. And furthermore told that she can row 2 miles an hour and walk 5 miles an hour. What we're asked is, where should she land her boat to reach the village in the shortest period of time? Any problem like this has a geometric aspect you always have to draw, because if you don't, you will never get yourself unconfused. So here's our little shoreline. Here's her boat. Here's Jane on the boat. This distance is 2 miles. And here, 6 miles down the coast, There's a village she wants to visit. They've got good snacks. So what are we trying to decide? What we're trying to decide is what angle she rows off at. Because she rows off at some angle here. Lands at some distance down some distance d down the shoreline. And then further walks 6 miles minus d. And so we want to know what will get her there in the least period of time. Well, how long does this take her? Well, there's 2 legs to this trip. First, she's traveling this diagonal line. How long is that diagonal line? Well, we can use Pythagoras' theorem. This is a right triangle after all. This is why you have to draw these things. If you don't, you'll never figure this out. So this is the square root of d squared plus 4 miles. 4 square miles, I should say, because we squared it in there. This is 6 miles minus d, and we know her travel time is her travel time down this leg, which is, remember, distance is just rate times time. So time is distance divided by rate. So it's her distance, square root of d squared plus 4 miles squared, divided by 2 miles per hour. We can quickly check our units here. This is d squared is miles squared, 4 miles squared, we square root that, we get miles. We divide it by miles per hour. Miles divided by miles per hour gives us just hours, which is perfect, using usual fraction math. So this at least has the right dimensions. But then she also needs a little bit of time to walk that last bit, which is 6 miles minus d divided by 5 miles per hour. So there's our total travel time. And it's a mess, as you'd expect. Can we clean it up at all? Well, sure. We can do a few things. One thing we can do is we can divide the 2 into the radical, since this is basically just a 1/2, so we can move that into the radical. We can take out the units, because we know this is going to end up being in hours. So this is going to be... It's going to be 1/4 d squared plus 4 inside a square root plus 6/5 miles per hour. Sorry, per hour. 6/5 of an hour minus d over 5. And we should be careful with units here. This is oops, the 4 has now been divided by another 4, so that's just 1. Remember that 2 has to distribute out into both these terms. Have to be careful. And this is just in hours squared, plus 1 hour squared. This d here is still in, so this is 1 hour over 4 miles squared, d squared. This is just hours, and this is d times hours over 5 miles. Okay, that's about as simple as it's going to be. Whatever you do, be careful not to make the usual algebra mistake people make when they have 2 things added up inside a radical. You can't split the radical over the sum. A square root of 2 things added together is not the same thing as the things added together. And you know that with numbers, right? The square root of 1 plus 1 is the square root of 2. Square root of 2 clearly isn't just 2. You can't split that out. That doesn't make any sense. Square roots don't distribute over addition. There's no property like that. So great, there's our formula. And if I want to be... Now, I was originally trained as a physicist, so you can sort of tell this because I've written units absolutely everywhere. We can simply... The other thing we could do is we could strip the units. We could just say that d is in miles. Just accept it. We can see the units are going to work out, so we can just write this briefly without units for a moment now. Now that we've checked our units. This is going to be d squared over 4 plus 1 plus 6/5 minus d over 5. So what do we need to do now? Well, we need to figure out how the time changes as you change d, as you change this landing position. How do we do that? Well, that's what calculus is for. We need to compute dt dd. We can do that The constant piece vanishes. This first piece is a little bit of a mess because we have to use chain rule. It's 1 over 2 times the square root of d squared over 4 plus 1 times the derivative of what's inside, which is 2, which is just d over 2. The 6/5 vanishes, that becomes minus 1/5. So dividing this through, we see we have d over 2 square root of, actually 4 now, because the 2's multiply together. Square root of d squared over 4 plus 1 minus 1/5. And we will find critical points. We want to know when is that equal to 0. That's equal to, well, we can add the 1/5 to both sides. We get d over 4 times the square root of d squared over 4 plus 1 equals 1/5. I know this is all kind of ugly, isn't it? Yuck. Can we do anything to make it prettier? Well, actually, yes, we can. One thing we could do is factor a d out of both terms of the bottom here. We can factor a d out of the radical. That gives us d over 4d square root of 1/4 plus 1 over d squared equals 1/5. Now we've just got one thing there. Let's multiply both sides of this by 4. We get 1 over the square root of 1/4 plus 1 over d squared is equal to 4/5. So just taking a reciprocal of both of the whole thing, we get, let's see, this is where we want to take another page. I'll cheat by crumpling that a little bit so you can see the next both pages at once. The square root of 1 over 4th plus 1 over d squared is equal to 5/4. I just took a reciprocal of both sides. Square both sides. 1/4 plus 1 over d squared is equal to 25/16. Subtract 1/4 from both sides. 1 over d squared is equal to 25/16 minus, well, it's 1/4, so it's 4/16. So 1 over d squared is equal to 21/16. We take a square root of both sides because our distances are positive, so you don't have to worry about signs. 1 over d is just equal to root 21 over 4, or d is equal to 4 over root 21, or square root of 21, 4 root 21 over 21. Oh, that's deeply messy. I'm hoping I didn't make a mistake on air. That would be embarrassing. How can we check this? Well, what is that number? What is 4 root 21 over 21? Well, I have a calculator here. Let's see if that's between 0 and 6, because whatever answer is has to be between 0 and 6, or else we're not doing anything sensible. Let me turn my light on here so we can see the calculator. There we go. What we have here is 4 times the square root of 21 divided by 21. Ah, that's 0.87. So what this says is we want to come in almost but not quite straight. If this is, now this is either a maximum or a minimum. That's the other thing we have to check. How can we check that? Well, one possibility is we can plot it. The other possibility, of course, is we can look what the sign does as we go across these things. We know what dt looks like. It looks like this thing back here that we originally set to 0. When d is 0, this is negative 1/5, so it starts negative. When d is 6, this is 6/4 or 3/2 divided by something down here. Let's plug in 6 and see what we get. Actually, yeah, let's do that. Plug in 6 to that mess, we get 6 squared in the denominator divided by 4 plus 1 So 10, square root of 10, we get about 3.16. Multiply that by 4, about 12. 1 over that, times 6, 0.47, minus 1/5, which is 0.2. We see it's positive at this point. So this is in fact a minimum. How do we, because it was initially negative, it goes through one critical point, and then it becomes positive again. So what we've now learned is that there is a minimum, and the minimum is at this funny point right in the middle. This minimum is at 4 at 21 over 21. This is Nighttime Mathematics Radio. That was actually a cool problem, because that's not an answer you'd immediately see off the top of your head. Now, of course, it's possible I made an arithmetic error there. I'm doing this live on the air. If I made an arithmetic error, if I made a algebraic error, so be it. That can happen. We can check our work later. We'll always have to check our work. But assuming my derivative was right, that doesn't look implausible. And we can actually check things like this in a lot of ways. One of them is we can check the original formula by graphing. And one way to graph, let's see if we can pull up a grapher for a second here. I'll shove a graph right in front of my own face. So hopefully now I'm streaming a nice look. Let's double check this for a minute. Oh no, sadly, we're not streaming what we want to stream. Let's see if we can start. Give me one moment here. Okay, we're back. And we're looking here at a nice little grapher window here. Hopefully. Oh, it's gotten a little big here. Let's make it a little smaller so we can see what we're doing. Just a moment, I'll shrink this window so we can see what we're doing here. Nothing quite like doing this live on the air, of course. There we go. Now this thing is going to assume that the things are actually called y and x, which is not always the very best thing to do, but that's alright, we can do that. Now remember, our original distance formula that we had written down was that the distance was, sorry, the time was the square root of the distance squared. I'm treating x now as the distance, because this grapher doesn't understand using variables other than x and y. All divided by 2. Plus 6/5 minus x divided by 5. We can plot that. And what we see is something looks very convincing. Let's scroll this over for a second. It starts right there on the axis. It initially drops and then begins growing again. And we can zoom in a little bit to try to see where we think that bottom is. The bottom is right in here, somewhere between... See, it's somewhere between... around 0.88 or so. It seems to be out where that is. Now, what is 4 root 21 over 21? Going back to our notepad, it is 0.87, which very convincingly looks like the bottom of this graph. So it looks like we got it right. This is Nighttime Mathematics Radio. Now I'm going to take a few minutes here to give people a chance to tweet in if they have math questions of their own they'd like to tweet. If not, I'll go on to another question that was asked me over the break in a few minutes. Alright everybody, we're back. Now let's look at another optimization problem that people asked us over the break. Now this one looks like this. So I can find it here. Yep, here we are. Sorry, I had to go through my filing system, which is a bit exciting. This one, again, is geometric. It says... Now, suppose a solid is formed by joining two hemispheres to the ends of a right circular cylinder. So you take a normal cylinder, like you see all the time. You just put little hemisphere caps on the ends. Give this thing radius r, height h, like usual. And they were told the total volume of this thing is equal to 14. We're asked, find the radius of the cylinder that gives us the maximum surface area. Well, what is the surface area of this thing? Well, it's got two pieces. It's got the surface area of a sphere, which is 4 pi r squared, because we've got two hemispheres, they've got the same radius. You can see we've got the entire surface area of one sphere here, and then we've got the middle part of a cylinder without little circular caps on the end. Remember, normally the surface area of a right circular cylinder is 2 pi r h, which is just the circumference of the circles at the ends times h, which makes perfect sense if you imagine making a little wrapper around this thing, which if you unwrapped it would make a rectangle with one side being the circumference of the circle, the bit you wrap around, and the other being h. But then normally you have two little circular caps, so normally you have this as plus 2 pi r squared, but the circular caps are covered up, so their surface area doesn't count for this thing. Now what we'd like to do is an optimization problem here, but to do that we need to take dA d something. We've got both r and h floating around, and that's a little unpleasant. But the good news is we know the volume. This volume, remember, is the volume of the cylinder, which is just pi r squared h. And there's no units in this problem, which is kind of ugly, but so be it. This problem, we do. It's cubic centimeters, cc. So this is 2 pi r squared h plus the volume of the sphere, 4/3 cubed. So now we have to solve for one or the other of these things, because our goal, well, actually we have two possibilities here, but the easiest is here. So what we'd like to do is say, well, what do we have here? Now, probably the easiest thing to do is just to solve for h here. We could say pi r squared h plus 4/3 pi r cubed is equal to 14 cc. So pi r squared h is equal to 14 cc minus 4/3 pi r cubed. Divide both sides by pi r squared. We get h is equal to 14 cc over pi r squared minus 4/3. The pi's cancel, and we have just an r left over. And we can plug that in for h to our area formula. So our surface area as a function of the radius only, which is after all what we're being asked to solve for, is 4 pi r squared plus 2 pi r times 14 cc divided by pi r squared minus 4/3 pi. I mean, sorry, 4/3 r. We can distribute this out to simplify a bit. That's 4 pi r squared plus 28 cc. The pi's cancel, and we just get an over r minus 8/3 pi r squared. And that's kind of cool because these two now are like terms, so we can just subtract them. 4 is, after all, 12/3. Sorry. Yes, 4 is 12/3. So 12/3 minus 8/3 is 4/3 pi r squared plus 28 cc over r. We now, this is a nice simple formula. We now want to take a derivative of area with respect to the radius because we want to find the critical points. We get 8/3 pi r minus 28 cc over r squared. And again, we want that to be 0 because we're interested in where the critical points are. And by the way, there's a limit to this thing, which we're going to have to look at later. And what I mean by that is when you get a radius big enough that the entire volume is just one big sphere, you can't make the radius any bigger than that. At that point, that's the limit of how big this thing can be. So we're going to have to check at the end that our answer makes sense, that you can actually get a height that's positive at our critical point. And generally make sure the signs are right. We suspect they will be, but let's see. If this is 0, well, we can multiply both sides by r squared. That will give us 8/3 pi r cubed minus 28 cc is equal to 0. 8/3 pi r squared is equal to 28 cc. R cubed, I should say. So we multiply both sides by r squared. R cubed is equal to, multiply both sides by 3 over 8 pi. 3 times 28 divided by 8 pi cc. And at the moment, I'm not. Now we can try to simplify this a little bit. 28 eighths is 14 fourths is 7 halves. So this is going to be 3 times 7 is 21 over 2 pi cc. And now at this point, so our critical radius is the cube root of 21 over 2 pi. And that's in centimeters. So how big is that? What is 21 over 2 pi? Pull out our handy dandy calculator. This is because now we're at this is as far as you're ever going to get with algebra. At this point, you really need to take a calculator into the game. we have here? We've got 21 divided by 2 divided by pi. Where's our pi button? This calculator, there it is. So we get r is equal to the cube root of 3.34 or so. How do we get a cube root? Well, notice up here we have a cube root button. Let's take this to second that cube root. And we get r is about equal to, we should really do about equals who's here, 1.495 or so. By the way, let's make sure this is right. Let's make sure we haven't made a mistake. I'll put this into memory for the minute. Stow 1. Now it's in memory 1. Now, recall 1. There's our number. Let's cube that. Times recall 1 equals times recall 1 equals, and there's that 3.34 again. So good. That was in fact a cube root. It's always worth checking these things when you plug numbers into a calculator. It's amazingly easy to make a dumb mistake with a calculator and have wrong answers for the rest of time. So this is a good thing to check. Now, is this actually going to be a minimum? Well, what is this? What is the surface area at the? Well, what happens at this point? Let's see. This is the point where the thing is 0. What happens if we go below that? What happens at 0? For example, if you plug in 0. Well, around 0, this thing blows. This term as r becomes small, this term becomes small, and this term becomes enormously large and negative. So the thing becomes very, very. So the area additionally starts very, very small, and it becomes very negative. So surface area is decreasing hard when the r is small. As r becomes larger, this term begins to go away because the 1 over r squared makes this term go away. This term grows because it scales with r, it gets bigger and bigger. So that dA dr will go from initially negative to 0 to positive again as this term becomes less and less important and this term becomes more and more important. So the result is, yeah, this will be a minimum. This is going to be a place where this is going to be a place where the derivative goes from negative to positive as this term ceases to control, this term begins to control. To make sure we're doing that right, let's look at a grapher. Now, looking back at our grapher here, this time we have our area was, remember, 4/3 pi x squared minus, second term, minus 28 over x. Or again, x here is r because this is a grapher. And I'll zoom out so we can actually see this thing again. We see something fascinating here. Oh, zoom, zoom. We see some truly wacky behavior. Oh, I'm sorry. I believe I mistyped this. We'll have to look at this another day. We'll check this one another day. At any rate, this is Nighttime Mathematics Radio. Okay, I'll take another break to let people have a chance to tweet in any questions they might have. For the moment, this is Nighttime Mathematics Radio. Howdy everybody, just one quick note from the thing I just did. Naturally I made a sign error in that last one. The minus was after we took the derivative, it was plus originally, remember? So with that plus, we get exactly the shape we'd expect, with a minimum right here at about 1.5, which is exactly where we expected it. This is Nighttime Mathematics Radio. So basically the only thing we did wrong was type a formula into the grapher at the very, very end. Once again, if anyone has any math problems, feel free to tweet them to @NightMathRadio on Twitter, and I'll try to help out. Okay, everybody, look, we're coming to the end of tonight's program. This has been Nighttime Mathematics Radio. Remember, feel free to tune in any Saturday night about 10 p.m. and we'll try to help you out with any problems you're having on the air. Feel free to tweet between shows, of course. That's where I get all these problems that I use the rest of the time. So if you tweet between shows, I'll try to help you out on the air as of the next show. This has been Nighttime Mathematics Radio, signing off. Good night, everybody.